So let's look at this example. Consider the following Leslie matrix L and the initial population matrix. Investigate the long-term behavior of the population. So to do this, let's go to the calculator and look at what happens over long term. Okay, so we're looking at the long-term behavior. So we need to define our matrices. So our Leslie matrix first. It is a 3 by 3. Put in our values. So we define our matrices. It's very quick to then look at what's happening long term. Matrix P and it is a 3 by 1. So let's look at L times by P to start with. So you can see we initially didn't have anything in our second and third age groups, and now we haven't got anything in our first and third. So let's go L squared times P. Now we don't have anything in our second. L cubed times P. Now we don't have anything in our last. L to the power of 4 times P. Now we're starting to get numbers in each one. So L to the 5 times P. They're increasing. Let's go big. Let's go L to the 10 times P. L to the 20 times P. And you can see now all the numbers are increasing. If I went L to the power of 50 times P, again, they're increasing without bound. L to the power of 100 times P, and now we've gotten huge. Okay, so our population increases without bound. So as we can see by looking at our investigation, we can scroll back and have a look, our population is increasing without bound. So our calculator investigation uncovered that our population increases without bound. So part B established numerically that the proportion of the population in each age group stabilizes over time and determine the long-term long-term growth rate of the population. So let's go back to our calculators and look at some long-term growth rates. So we're going to look at the population after 25 years and population after 26 years. So let's go and do that. Now, if we want P of 25, we do L to the power of 25 times P. And there are our populations. If we did P of 26, so we got L to the power of 26 times P. And now we can use those to work out our rate of increase. If you did them on your calculator, you can copy and paste. Okay, it does say to look at each time period. So the first time period, it's a rate of increase of about 1.19, which is 20%. Oops, which is around 20%, 19%. I've got to copy the other one. Divided by, go up and get our other value. So the same, final one. Oops. So for each of them, it was approximately 1.19. So population is increasing by 19% each time period. We could have also added the overall populations for each and did an overall growth rate, which would have to be the same of 1.19. So for P25, we had L25 P0. So, and that gave us 34,781.25, 7297.85, and 3062.50. And for 26 years, L to the 26 P of 0, we got 41441.41, 8695.31, and 3648.93. So if we want to look at a long-term growth rate of the population, let's look at our rate of increase. Forgetting letters in my words. So rate of increase for our first age group, it's going to be 41,441.41 over 43,781.25. And that gives us approximately 1.19. For our second age group, 8,695.31 over 7,297.85. That gives us approximately 1.19. And 3648.93 over 3,062.50 also gives us 1.19. So this indicates that the age group proportions have stabilized by the 25th time period. The long-term growth rate is approximately 1.19, and the population is increasing by 19% each time period. Following on from this, often we find after a long period of time that the proportion of the population in each age group does not change from one time period to the next. We can find a real number lambda such that our Leslie matrix times by our population after that long period of time equals lambda times that population. Okay, so that's our growth rate.